Welcome to lecture 10. We will choose a new topic called code concatenation. That's a very fundamental operation that you can do with respect to codes. It's something which most of us computer scientists are very familiar with. It just is trying to understand recursion in the language of codes. And the idea is powerful enough that by the end of today's lecture, we will eventually construct good codes using the material that we have done so far and using the technique of code concatenation. So let's see where we are right now. Let's recall. Yeah. So we constructed, let's look at these amazing code called Reed-Solomon codes, which are basically n, k, n minus k plus 1. They meet the singleton bound. So all of this is amazing about them, except the key thing about drawback about them is q. The alphabet is very large and q has to be larger than n. The key drawback, that's the drawback of Reed-Solomon codes. If this was not there, Reed-Solomon code fits the. It's amazing in every aspect of that. Meets the singleton bound is the best possible. You have efficient algorithm, extremely nice algorithm that you can do. You have uniquely put up to exactly half the minimum stuff. But the main disadvantage of the Reed-Solomon code is that the alphabet needs to grow. It's not just not the binary alphabet; it's actually a growing alphabet. The larger block lengths you need, you have to be at least n. The MDS code, actually one of the projects is to ask in the MDS conjecture, there is, if the code is MDS, how large should the alphabet be? And the alphabet has to be at least n. You can show this. You can't, it's not as if any code that meets the singleton bound has to have alphabet sizes that are going. You can come up with code which almost meet the singleton bound, that is 1 minus epsilon fraction. There you can get lower codes with smaller alphabet, but still growing alphabet, not n, but possibly slightly. Yeah. Have these codes. So let's look at a specific instantiation of the singleton of the Reed-Solomon code, because what I want to do is, so what's the goal of this lecture? I want to find out, I have this code with an amazing distance and rate, but over a large alphabet. Our goal is to now reduce the alphabet and come down to the Boolean alphabet. So what can we do with this? So just to make things like simpler, let's assume the field is actually some F2T. And n which we are operating, the set of evaluation points, yes, is F itself. It's the entire set. So you're evaluating on this one. And let's for assume so that is n is equal to q, which is 2 per t. And let's assume k is n by 2. So we are working with something like so in this setting for these parameters, for this setting of parameters. The RS code is what is the final block length is n, the dimension is n by 3. What's the distance? It's n by 2 plus 1. I'm going to drop that 1 as that's a lower bound. The alphabet size is 2 per t and n is 2. So that's the code. The thing's nice about it. It has constant distance. The alphabet is the one that's now because it's over JF2, so the field was F2 to the T. Of course, we know that there's an isomorphism between this and F2T. So we could think of each. So we have a collection of code words of the block length n, with each symbol comes from an alphabet of size 2 to the T. You can just write it as, instead of writing as a large alphabet, you can write it now as a T. Each thing you can write it as a T-bit string. And now look at the new collection. So now just write the raw encoding, write down each symbol. So you have this long. What do we have? We have this ensemble code word. Block length n. Each element here is each. So you have alpha 1, or rather C1, C2, and Cn, and each Ci is an element of F2T. So that's isomorphic to F2T. So instead of viewing it as an n, this one, I can also view it as this n is over the alphabet F2T. I can also view it as an NT long string over the alphabet F2. Now you could ask, what is, when you view it this way, what's the corresponding distance and stuff? And because we had chosen F2T, this continues to remain linear. So take the addition of two codes, it will still remain linear. That's the only thing you need to check for F2 linearity. There's no multiplication by scalar. The only scalars are 0 and 1. So it's still a linear code. So let's look at so how does this code? So we just write out each element of F2T in its raw encoding. That is a bit string of length T. What do we get? We are going to get, let's look at the code now. It's going to be, the block length is NT. It's a linear code as well as square parameters. What's the dimension? It's now we're going to talk about it in the smaller alphabet. It was n by 2, but it was n by 2 symbols from the large alphabet, which corresponds to NT by 2 symbols from the small alphabet. So, because everything is going to go in terms of the small alphabet now. Okay. That's good. So the rate is amazing. So the rate is fast. It retained the rate from the code above. What about the distance? At least n by 2. All that we know is if two code words are different, then you know on n by 2 locations they are different. So n by 2 large symbols are different. Now, if two large symbols are different, all that you know is one bit is different in the corresponding this one. Therefore, you only get n by 2 over here. So the point is this doesn't drop, and but it's now over the Boolean alphabet. So there's one catch over here. This is not true for all T. If it were true for all T, then I would set T to be 1, and I've got an amazing code. T is log n. This is true only for T being exactly log n. Therefore, now writing it, this is n log n by 2, n by 2 T code. Or if you now call n being equal to n log n, this is roughly like n by 2, and this is approximately n by log n 2 code. Okay.
Log of small n.
Huh?
Log of small n.
No, log of I have to shave off. So n is n log n. Therefore, this is n log n. So I have to shave off.
It's log of small n.
It's a log of small. No, but log of small. No, it is log of small n, but up to constant log of small n and log of capital N are the same. Yeah. So I want to write everything in terms of, because that's a log n factor. So I'm going to ignore constant. So it is some, probably put a C here. So what's happened in this process? The rate has remained half, which is still amazing. The distance, which was originally very good for the read Solomon code, by the time we came to the Boolean alphabet, the distance which was constant has come down to 1 by log n. So you are nicely in the. It's no longer a. It's you're no longer in the region. You're in one of the extreme points once again. You're in the curve. We wanted to get a code which has constant rate, constant distance, and here the distance is going to 10%. The fraction distance is 1 over log n. So this is not a thing. But you look at it, there's something fundamentally naive we are doing over here. We should do something better out here. What can you suggest that we do slightly better off? We want to come to the Boolean code. We want to talk about code of the constant size alphabet. Let's go all the way to Boolean alphabet. So what's happening over here? So the key observation, notice is actually a very simple observation, but crucial observation. What are we doing? We're taking each symbol in F2T, the field F2T, and writing it as a T-bit string. In some sense, we are writing in the raw and encoding. We are writing it in the natural. You could use a code over here to do this. You take a T-bit string, use another code to you take a code which takes a T-bit string and maps it to say some 2 T-bits or something. You could think of doing it. For example, so you had, let's go back to this picture. So right now I didn't change. So I had this thing over here. Suppose we had an inner code which took T-bits to 2 T-bits. Right now, we took a thing which took T-bits to T-bits. We just took the match coding. Suppose we put this, and suppose this code had 2TT and say 0.001T. I haven't told you how to get this code, but suppose I managed to I have this code. Now, suppose what I do is the inner symbol, I do it as a T-bit string, but I don't write down. So the idea here is going to be use an inner code to encode the symbols of F2T. That's the crucial idea. Might get you to food. Okay. So then what's happening? What are we going to be doing? We have this object over here. So each of this itself is blowing up to a 2T. So this was T bits long. This is blowing up to 2T. And so on. So in some sense, what's happening? We had a we started off with a n by 2. Each of T bits long. We applied the read Solomon encoding to get an n long thing of each of T bits long. That's the first step. And then each of them, these are actually symbols of the large alphabet, but we viewed it as a T-bit string, and then use the small alphabet. So right now here we are now doing the Cin. So and that's the final object that I'm going to get. Yes, yeah. Yeah, so that's a catch, but we'll see why is, so yeah, so I'm assuming Cin is this, which is already I'm assuming that the code which I want to construct, I'm assuming that those codes exist. So let us see why that assumption is this one. But first, let's find out what the difference of this code. And then I'll come to why that assumption is a fair assumption to make. Why? It's not a cheating, but I'm assuming what I want to do. I'm assuming, but if such a code we don't yet know how to construct. That's a code with constant rate and constant distance. That's exactly what we want. But yeah, that's true. Things I'm assuming what I want to do to construct. So whatever code which I get is actually going to be weaker. It's going to have weaker properties than that code. The question is why is this okay? Let us but before that, let us see what is this code? How many? What's its distance and all? So its input is nt by 2. In the bit world, it's nt by 2. That's the dimension of the input space. That's the starting. What's the final? 2nt. So now we have the rate has possibly gone from half, it's become 1/4 now. But what's the distance of this code? Yeah, so basically, we know that if there are two code words which are distinct, they are going to be distinct in at least n by 2 locations here. Now, each of those n by 2 locations, previously, if you were the raw coding, you could only say they were differing in a bit. But now, because you're using an encoding, for each of those n by 2 locations, you know that they differ in 1000 fraction of this one. Therefore, the final code which I'm going to get is actually going to be so I'm going to get n by 2 locations in which at least I'm going to have different things. And for each of them, I'm going to get an extra star 0.001 t. Okay, so now finally we have a 2nt by 2. What was this? 0.0065 nt. So this code does have constant rate, constant distance. As Sridhar pointed out, it's actually weaker than that code. So it has rate 1/4. Its rate is weaker than that code, its distance is weaker than that. But have we gained anything in this process? You have gained a larger block length. But what is the larger block length value? So notice how did one construct such a code? The 2tt 0.001. The only way we know how to construct such code right now is Gilbert or Wasserman. That is pick it greedily. This is a very expensive operation. The picking greedily, you have to search over the space of code words and then find out the code. But because t is small, you have time to search over this space. You are not running in time for exponentially. The search is going to take exponentially in the block length. Exponentially in t. The focus t is much small, whereas you are allowed polynomial in n. If t were logarithmic, then in principle you should be able to search for this code and find this code and then plug it into the function. So that's what Forney's concatenation buys you. That is, yes, it's still not fully satisfactory. It's that also by the end of the lecture. You count for the code super. They won't be able to do for search operation at all. You remove this, but Forney says that yes, I don't know how to construct constant rate, constant distance codes. I know that they exist. I can do a brute force search. Well, it will take me exponential time to do this brute force search. Can I exploit the fact that I need to do this brute force search only on a log n size problem and harness that to get n sizes? And that's what Forney is trying to do. Forney says he wants to construct codes of log length possibilities on capital N, which is 20. T will be chosen to be logarithmic in n. And now you have to search if there's a good code in this space. You have time to search. So that's Forney's code concatenation. So let's formally write down what Forney's code concatenation is, and then write down what exactly are the parameters he will get. Clear? This is just recursion. That is, you have a code. You're doing the first time one encoding of the code and then again another encoding. You could have tried to do it with the same code possibly. We are doing two different codes. So we will actually do it formally more generally. So we will see that over there. So let's define code concatenation. So we have two codes. We have an outer code C out, and code concatenation does not have to have be linear. We kept it linear. Code concatenation can be very fun. So suppose we have an outer code, which is right. So it's an N K D code over the alphabet Q. So alphabet code. And we have an inner code Cn, which is N small k small d over the alphabet small q code. But the only way that the two codes should be talking, so every alphabet here should be sort of the input for this. In other words, we must be able to, with the condition that Q is an alphabet symbol here, that should look like the input message. Q should be equal to Q power K. So that's the concept. If you put these two together, I want to combine to get the what I call the concatenated code. What? It's fine. Actually, capital Q is going to be equal to. Yeah, but you want to keep small q as small as possible. So you choose to make it as small as possible. You just need to be able to do the input. And yes. The same picture which I'm going to be drawing again. You have this. This is over the large. This one, this is of size capital K. You use first the C out to encode this. You're going to get this larger object over here. These are the symbols from Q. Both these. This is and now, so that's the first encoding. Now you reinterpret each symbol over here. This is just a raw encode. What you're going to do now is just this is just a reinterpretation that's going to go on here. You just take this then. Reinterpret this, but now you don't, you knock out. You interpret this not as a, you interpret this as an n. How many bits? Now it's an n small k. This one as symbols from small q. That's it. You just each symbol over here was k bits. You think of it as not a q-bit string, the element from capital Q. You think of it as a k element string coming from small q. So now you view it as an nk. This one, and in each of these chunks, you sort of apply the for each chunk, for each of these, you apply the inner input. That's each of these processes. See. the total one will now be n. Okay. So once again, so let's look at it. Concatenated code C. So what is its? What's its? So it's not a. What's the total number of code words here? So what's the initial input? It's k times k. What I want to say is capital K times k is the in the alphabet of the smaller guy. It's k times k. I want to write everything in the smaller alphabet. What's the final block length? N times n. What's the final distance? D times d. Yeah, times d. Why is that? Answer Ishan's question. So take two messages which were different. Now, if you import them using C out, you know that they will be different on at least capital D symbols. The remaining n minus d symbols, they could be exactly the same. Now, each of these capital D symbols, you're applying the inner code. They will, so in each of those locations, there will be another D response. So for each of these D, you're going to get another small d. So therefore, totally you will get d times. Therefore, code concatenation very behavior. It's basically the block length multiplies the block length product, the dimension of the product with the symbol. And furthermore, if Q is FQ and capital Q is FQK, the field extension of FQ and C out and C in are linear over their respective fields. So is C. Yeah, so that's it. It's an extremely simple operation, but it's a very powerful operation. See what we have. And 20. That clear? Seems like a very simple operation, but it's powerful. We're going to get it finally. It's got us with more or less. And we'll see this operation over and over again. So the way says, even though read solvent was bad with respect to alphabet size, you can use it as a good starting point all the time and then appeal to code concatenation to get good codes eventually. So, how to construct good codes from by using code concatenation. So we sort of hand wave this. Let's see it a little more formally. So basically, what we are trying to do is we are going to take outer code. We need a code which is as good as possible. Read Solomon is the best. It meets a singleton mode best you can do. So take the outer code to be the read Solomon code. The inner code, we are going to want to pick up a code of what's guaranteed by Gilbert or Harsha. But we need to ensure that the time to find the inner code is polynomial in the side in the outer codes in the total concatenated codes block list. That's what we want to do. So the one is find inner code, find C inner, a good code in time poly n. If you can do this, then you are done. Poly n. I'm okay to run. Usually poly n will capital N will be the same as poly 1. So the final block length is nn, and you want to be just running in poly nn. Now, how much time does it take to find So it's easier to search in Washroom style, searching for linear code. How much time does it take you to search? So typically, you find a good linear code. So it takes via using Washroom technique, using what we did in class. Washroom technique. It takes Q to the order Kn. If you want to find a code with dimension K and small block length N and alphabet Q, this is how much time it sort of takes you. Because that's the size of the generator matrix. You have to go over all possible generator matrices of this one eventually in time. So think of Q, small q as 2 for us. N is, what is N? N is log N. K is also sort of log N because K, this is the small code is going to be like a constant rate code. So K will be some C times log N for C being less than 1. So this is 2 power log square. That's not polynomial in N, that's N power log N. It's not polynomial in N log N. The final log length is N log N, capital N log N. So this gives you roughly, this is for our set for C out being read Solomon and C in being as above. The time taken will be so N will be equal to N will be theta log capital N. K will also be theta capital N. The time will be 2 power order log square theta log square N, and that is something like N to the power order log.
So the angular reading construction will also from order 2 power t whole square.
Which one?
So we first take a code word,
Yeah.
then mark its d ball as value.
Yeah.
And take a code word, mark its d ball as value.
Yeah. Yeah, but that's the same thing with the K2T square is more or less the same as
Okay, but here now you are marking each string at most once.
yeah.
So then within that or polynomial.
So you have to so you can do this. You have to be very careful about how you are doing Gilbert's greedy. This one.
Yeah, so at each point when I click a new code word, I
Yeah.
will mark the d ball and only. This will take time almost 2 power t.
Okay.
And at each iteration, I will pick a new code word and then mark its d ball.
So you have to do This is exactly so you have to do Gilbert's greedy construction. So the way around this is basically Gilbert's greedy construction. What you're claiming is that can be done in Q power theta n. Q power theta n, and this is okay. This is fine. This will give you then this will be 2, this will be log n, and this will be for now. So in this, so you need to do which is basically what theta to say to do Gilbert greedy construction carefully with some bookkeeping. It's not hard to do this. Then you get this, which is poly in capital. You can get it. You have to keep marking off which of the on the space you have to when you're doing. How did Gilbert's proof go? You took you started off with an arbitrary thing. You took off a ball of radius t around radius d around it. You have to mark off these, and then go once again search through the space to find another point. So you basically have to do whatever greedy which we did in a very careful fashion, so that you don't cross Q to the order. Okay. And it can be done. This is good. So is this satisfactory? Is this satisfactory? So is this so? Of course, it just answers certainly better than anything we have. So far at the end of this, we have an explicit code. Huh?
It won't be linear.
It won't be linear. It won't be linear. So you have to go and do the same bookkeeping watch level for Harsha. I think that can also be done. But I want to mean neither of this is fully satisfactory. And what is unsatisfactory? Somehow we are doing this brute force search. So claiming that for every n, you want my code of plot length n, I'm going to sit and go and do a brute force search. Yeah, it's explicit in the sense there is an algorithm of polynomial time that outputs this, but it's not as a nice code as Reed-Solomon code or Reed-Muller code or any of these codes which I output. There's a nice algorithm. There's no element of brute force search going on in any of these. Of course, this is all I'm just being qualitative and being very subjective and saying that this is not a good construction. Question is, can I make this formal, this objection that this is not a good construction? Compared to, I want to say Reed-Solomon, the other codes, BCH codes which you have seen, are nicer constructions. They are somehow more explicit than this construction. So what will come is the notion of strongly explicit. Reed-Solomon has the property, so firstly they are linear codes. So what I want to say is about construction.
What are we careful about? We still kind of look over all possible code.
No, you just need to ensure that the whole process you run in time due to the order. Above construction is explicit. But still involves brute force search. Which is not such a nice aspect of this one, but that's just there's an algorithm that does the code. What more do I want of a code? The code is, I've given you an algorithm for every n. The algorithm runs in poly n, which outputs the encoding process. What more do I want of the witness? And the thing is, we can ask more. I want to say the codes which you have seen so far, the algebraic codes which you've seen, have an even nicer property. They are what's called strongly explicit. What is strongly explicit? So this. Codes. So code is specified by a generator matrix, which is what? Which is this. K by n. This way should be longer. It's a n by k matrix. So what I want, so the code is explicit. So far, we said the code is explicit. If I can lay my hands on if it's linear, I can lay my hands on the generator matrix in time poly in n. Can ask something more. I give you ij location, and I say, so I give you a particular run and a particular j, and I tell you what output the ij location of generator matrix poly in ing, the bit representation of ing. So strongly explicit is. So I'm going to define it only for linear codes. I'm not going to define only for linear codes. So given I in n and j in k can output g comma ij, the ijth element of this one, in time poly in the input now. Poly, that is what? Poly in the bit representation of I and the bit representation of j. So it must, that means in particular these are like concentrate code, which is poly in log. So I'm not, that is typically poly in log n. It's always log poly, it's poly log n, because I is going to be logarithmic n. That's a bit. If we want this generator matrix, this is take an arbitrary location, I must be able to output that in poly log n time. And if you look carefully at Reed-Solomon and all, what was Reed-Solomon? I gave you a generator matrix, I gave you the generator matrix for all these codes explicitly. If you're telling me a particular location, you can go and compute that. So exact all the codes that we construct, all the algebraic codes that we construct actually have this property. So the algebraic codes Read Solomon, BCH, read Muller are strongly. Whereas the above construction of four. Huh? I gave a parity check. From a parity check matrix, it's easy to come up with this. For BCH codes, how to I didn't tell you, but you can come up with you can't, I don't think that's not always true. That's not always true, but with BCH, I can just give you the generator. We didn't do this for BCH. Is it easy to do this for BCH and come up with a generator matrix? I don't know it off the top of my head, but it should be super explicit. They can't say anything non-explicit about BCH. So, or do it the other way around. So define strongly explicit in terms of parity check matrix. You can define it to one of the two. That is, you get a good handle on the code somehow. These are, let me drop this off. We haven't formally proved this in class. And the objection to the given code is Forney's code content, though it's a good code, it beats in terms of goodness, it beats all the code construction. It's not strongly explicit. Question is, can we fix this one? And what we will do in the remaining 40 minutes or so is actually we will come up with, we will use concatenation to come up with good codes which are also strongly explicit. Concatenation is a very simple idea, a beautiful idea which gets you exploits the large code. It reduces the problem of searching for a code to a much smaller space. So now you can run a brute force search, get that code, concatenate it, and you get the final good code that is. So before we go to strongly explicit constructions. And the reason strongly explicit might say is that between finicky and sometimes these codes are such large objects, you're writing these large objects, you want to be able to just output one location or something. You want, so I mean, okay, right now it's just an object. It's one way of stating why I can sort of say, it's sort of articulating why I'm not yet fully satisfied with that with the above construction. There is an element of brute force search which I have to do. And this one, it's not as explicit a construction as read Solomon. The question is, can I make it as explicit as this one? And we will see that. I'll give you another construction which is super explicit and will be a good code. And you will see the difference. There won't be a brute force search element. Some sense there will be a brute force search element in the construction, but I'll push the brute force search construction to the proof, not the construction. So it will happen in the analysis and not in the one. And you'll ask, see, it's quite an interesting idea. But before we go to that, I want to now recall what we have. Go back to this picture which we had, the graph plot. So we had this was delta, this is R, and we had Gilbert Wasserman. This is the question of it is out there. The type is half. And question is the code which I'm going to construct now, where are they? So we have constructed good codes. So Gilbert Washington that these are the code which I constructed going to be weaker than the Gilbert Washington. But I'm using as inner code the Gilbert Washington codes, and code concatenation is going to mitigate both the rate and the distance. So it's not going to be a point. It's going to be a lower point. Question is where does the code will be constructed now? I'm going to that. So let's actually plot the curve, which the codes which we have constructed this. The question which I'm going to ask is, what are the explicit codes or delta trade-off? So what is the R versus delta trade-off? Achieved by the above explicit construction. So we're actually just going to go into the inner workings. We're going to take the outer. We need to take a suitable choice of outer code, suitable choice of inner code to do the whole thing. What's the best outer code you do? You pick up Reed-Solomon code. So C out, we'll choose it to be Reed-Solomon code. So suppose we pick, so then we can choose delta out to be equal to 1 minus R out and get it. So if you choose Reed-Solomon, you get the best trade-off. There's a small little of one term, I'm going to drop it off. So you can get delta out to see that. So the outer code is the code which we will take. The inner code now, because we can do the user the Gilbert construction. You can get a code with what can you get? You can get delta in to be greater than or equal to H2 inverse 1 minus R minus epsilon. That's the so R plus H2 delta is always greater than 1 minus epsilon. So you can basically get this thing. So let's now put them together. So the concatenate. What?
The H2 inverse you mean the being like
below half. Okay. So not the yeah. Concatenated code. So its rate R is R out, R in, smaller. Yeah, just to keep it like that. And small r. And delta is delta out. And delta in. It's at least so much. So let's write delta. So delta is at least. So let's go to. I want to write I want to eliminate. So there are multiple R out delta is. I want to write everything in terms of delta and R. That's the final code. I want to write what's the delta R. Don't have all these parameters. These are just things which we used along the construction. We want to. So what is delta? So delta out over here, I can make it 1 minus R out. So 1 minus R out itself is R by R. So the only parameter I'm going to make, I'm going to ensure is I'll only keep R as a parameter. I drop out all the other parameters. So 1 minus R by S. So this is delta out is delta. Delta is greater than delta out. Delta out itself is 1 minus R. R out is R by R. So this first term is this. The second term is H2 inverse 1 minus R minus epsilon. And I get to choose R. Therefore, it's basically what you're going to get at the end of this is delta is greater than or equal to max of R in 0, 1 that achieves this. So this is what the above construction more or less is going to give us. So this is what is called this calculation was done by Zyablov.Zyablov's.
So we know which smaller optimizes this. We know which smaller optimizes this.
So it's not a nice function. You can plot the curve. So what happens is if you go back to this picture. That's this was that's Zyablow's curve. Zyablov form. You get such a picture. You can plot that curve and do it. It just says now. So if you care about explicit codes, so the GB bond is a code in which we know that code exists. The achievability code. Now we know not only such code, we also on the dark green curve, we also have these explicit codes along the dark green. So everything that I did actually could work for arbitrary alphabet. It will only change from the 2 will change to 3. So the outer code will still use the read column. The inner code will just use the Varshama construction, but it will be delta and greater than H2 inverse 1 minus R epsilon, and it will be the same picture. It's always considerably smaller. In fact, so if you can look at one you can ask at around half, and then the difference is half minus epsilon. What does the GB bond give you? The GB bond gives you codes with rate omega epsilon square. We saw this calculation. What does the Zyablov bond give us? If you actually look at this one, it's not a hard exercise. You can find out. It will give you omega epsilon cube. The rate of the code will be considerably smaller than what the. So everywhere for the entire region, the Zyablov bond is considerably below the GB bond. But of course, here you're getting explicit codes. So we still don't know things on the GB. So right now, at least we've gone all the way up to the Zyablov bond. And the code concatenation lets you get. Okay. Questions so far? The next question is going to be what about strongly explicit codes? Let me Zyablov. For right now, strongly explicit codes, just strongly explicit good codes. I don't care whether I'm making Zyablov bond or strongly explicit. They haven't yet constructed these codes. Yeah.
If I first forget maybe the intermediate
Yeah. So this should work. The recursion. Check you do it.
other parts for intermediate stage and
So think of it. They never managed to make this work. The other question is actually can recursion get you all the way down to a constant set of good code? People use read Solomon again and again, and then you can keep going. We don't know how to make this work. It doesn't even give you a good code. Forget about it. Doesn't give you a good code. I don't know. Give me a point in the which is not.
Mostly I think brute force and
Oh, okay. One of them you're going to do it that way. Yeah, then you this one. You can omit it, but each time you do this, you're going to go because code concatenation is a nice. The advantage of code concatenation is you're able to exploit, do this sort of search for a smaller problem, but actually it's bad with respect to rate and distance because both the rate gets deteriorates and the distance deteriorates. It's all the code concatenation always worse off than what because it's a product of the rates and the product of the distance. So you get a worse off rate than what you started off with, both with respect to the outer and inner. Therefore, it will be much lower than the Zyablov. So this one. You could come up with strongly explicit by taking Reed-Solomon, go another level of Reed-Solomon, now make the input size log n, and now do brute force search over there. So that's what that is for. It will give you a strongly explicit code because now it will give you a strongly explicit code, but it will go considerably below the Zyablov bound. So there are two levels.
it's always optimal to give down to the target development space beyond yes.
In fact, it's not. It's optimal to get the alphabet in the first shot itself. So if you want to get the GB bound, I don't know any code concatenation process will do this, or you have to ask for other levels. Given is there a distance amplification process? So we haven't seen these. There are such. Given a code, can I amplify the distance? Seems hard. There are some ways of doing it in certain context. If we have time, we'll see this later on. But right now, I don't. You're given a code with a particular distance. Can I construct a code with a larger distance using this? Some process. Take a process, you take a code and you get a code with a larger distance. Yeah, we will ask these questions. It's not well defined here. We will see this later on if time permits. We'll go into some of these. Right now, all the operations which you are doing are deteriorating both rate and distance. So the question is, can you sort of improve one at the slight cost to the other so that you can come back whatever you lost out of code concatenation, you can push it up back a little bit. You can ask these questions. But we still don't have fully satisfactory answers. Recursion, who thinks that eventually recursion, and not do any brute force search, you can come to a very good code, but we don't know how to do this. There will be an element of brute force search. Even the next construction is going to have the one which I'm going to go strongly explicit. Just going to have one level of concatenation. It's going to have brute force search, but the brute force search will happen in the analysis, not at the code construction. It's quite. I think this is going to be what we're going to see is Justesen's construction. Of course. Look at Justesen's code. Let's go back to this picture, which we can do. So how did code convert? We had an outer code CO, and then we used an inner code CN to do the concatenation. We needed the outer code to have rate but that we have the Reed-Solomon is the best of it. So outer we have the best of it. Inner, the problem was with the reason we didn't have explicit code was the inner we had to search for the best inner code, and this was what process made it non-explicit, not strongly explicit. Now, so what's Justesen? Justesen observed that out here in this construction, in the proof of it, nowhere did we use the fact that you have to use the same inner code for all the capital N locations. You could use different inner code as long as each of them guaranteed distance. There's nowhere in the proof we use the fact if all the inner codes were NKD, small n, small k, small d, the proof just goes through. There's no reason we had to use the same inner code for all the. No. Okay. Now we are only made my problem harder. I'm saying I need not just one good inner code, I want so many inner codes. Then if you look at more carefully, what we need is not, we don't need all the inner codes to be good codes. If most of them are good codes, that's good enough for us because if the fraction of the number of codes are small, which are bad codes, bad inner codes here, those places we will not get distance, but all the rest will get distance. So what we do is the group for search, basically we list out all possible inner codes. And we know with high probability these codes, if we have a small ensemble of inner codes, so that most of them are good codes. I do not know which ones, but most of them are good codes. Then still Forney's code concatenation idea goes. Okay. So once again, what's the idea? Just looks at this picture and he realizes that to get the final form, I'll formalize everything by recipe. What he observes is first we don't need all the inner codes to be the same code. There could be different inner codes. All of them, as long as they were all NKT Q codes, they are good enough. Then he observes not all of them have to be NKT Q. Most of them are NKT Q codes. Suppose epsilon fraction of them are not NKT Q codes. That will just reduce the distance by 1 minus epsilon factor. Because you had D blocks here which were different. Possibly epsilon of them are bad inner codes. So those codes you won't get, but the remaining D into 1 minus epsilon, you are going to get your D minus epsilon and you are going to get distance. So all you wanted was a construction in which most of the inner codes are good. So we are breaking our code is going to break down into two parts. We are going to first show that if most of the inner codes are good, then even then code concatenation work. We try to understand what will be the distance of the final code we get. And then we will give an ensemble of inner codes which are super explicit, in which I won't be able to prove that this particular inner code is a good code, but I'll show that most of them are actually good inner codes. That's Justesen's idea. Justesen's idea is a very clever idea. He throws the brute force search into the analysis. He says, the fact that I'm going to put down all possible codes. Most of them are Hilbert and Wasserman's construction also gave this. They said most codes are good codes. Most the codes are good codes. So basically, he said I just use all possible codes. I had to give an ensemble of codes. Most of them are good. That's enough for Forney's construction to go through. This is the idea. We'll make everything. One is sufficient. It's okay. Yes. Inner codes are different. This seems to make the problem harder because we need not on and sufficient if most inner codes are good. And then construct an ensemble of inner codes such that most of them are good. Okay. So this is an idea. This is an idea. Here he uses, he credits this construction of ensemble to Wozencraft ensemble. The ensemble will show as an ensemble to Justesen credits it to Wozencraft. So let's write down both these. Segments. So the first proposition I want to say let C out be a NKD Q code as before. That's the one. None of this needs to be linear. And we are not going to have one inner code, we are going to have you're going to have C1, C2, we're going to have N inner codes, one for each of the or ensemble of N, K, Q codes. That is, right now I'm only talking about the dimension and the rate, where Q is equal to Q per K or greater than Q per K, such that at least epsilon n, at least 1 minus epsilon n fraction, epsilon n of inner codes have distance small d. Then which is C out composed. I should have used this notation. People use this notation sometimes. Not standard. C is C out composed C. It's not standard. Here this is not composed with one object, so composed with this ensemble. Yes, sir. Is a and the block lengths are as before. What I'll have to put is the distance. So we'll see the proof and then put that on. The analysis is not so. Let's take two M and M prime, and M prime belong to Q to the KK, and such that M is not equal to N prime. Q to the KK, or it can also be used as Q to the capital T. So what do we know? We know by distance of C out, delta C out M, C out M prime is at least capital D. That's what we have. Now, these D could be anywhere in it. You're possibly losing out on epsilon n fraction of this one. Therefore, but for the epsilon n fraction, epsilon n of the inner codes, for epsilon n of the inner code, you know that this distance, with all the rest, you continue to get distance. Therefore, since all but epsilon n of inner codes have distance at least d, what will be the distance of the final code? This, so just delta the concatenated code C of M prime is going to be at least d minus epsilon n and times d. So So as long as this B was a constant fraction and epsilon was a small number, you still more or less get dt. That's what. It's a very retrospect. Once you realize the idea, it's simple. This proof is trivial. That's basically Justesen's idea. We have to now implement it. I need a inner code. What's an inner code that is going to have this? And I want the inner code because eventually I'm interested in explicit codes. I want the inner code to be as explicit as possible. So the question now is, what is input ensemble? Wozencraft. So we'll be able to construct ensembles for codes, a whole bunch of inner code with rate at least half. I'll give the case, I will only do the case rate equals half in the lecture. You will be able to extend this for everything greater than half. Do things less than half, things are a little more problematic. You want to do it in lecture. It wasn't first example. So here, I'll do it for a specific set of response. We will view n here to be I view it to be 2t minus 1. Therefore, I will view the I'm going to take a very specific setting. I'm going to take the outer code. I'm going to construct for a very specific setting for the outer code. I'm going to construct a code ensemble of inner codes. The outer code will be the outer code I'm going to construct. The outer code is going to be Reed Solomon. Reed Solomon. The field F being 2 to the t. Yes being F star. That is n is 2 to the t minus 1. And let's k being k could be anything. Think of k being n by 2 just to keep things fun. It could be anything. This I don't care about. Actually, let's keep the outer code to be have out. Let's keep it. What's the inner ensemble? So for each alpha in F star, we are going to define a code C alpha. That's going to be the inner code. Corresponding. What is the inner code? So the inner code C alpha is going to be something from 01t to 012t. It's going to be a code of this type. So you have for each of the, so we have for every element, as many as the log length of it, you need to construct a code for each extra. What's the code here? So we'll view this as now we can go back to viewing this as F2t, these tables. And what we're going to output is F2t squared. 2 elements from this. And what's the code? Code is just going to be x. I'm going to give it x and alpha x. Just multiply it by the field element. Okay. So that's the inner code. Okay. So what's we have to prove something with the input. But for the inner code, once again, when I go back to this, I have to go back. So this is thinking of it as a field element. I'm doing multiplication in the field one, and I'm going back to the Boolean representation. So C alpha as a code depends very much on which representation for the field I use. Notice, because I need to show that this is a linear code. Certainly for every choice of alpha, this is a linear code. Even when I do it over the binary alphabet. But what's the distance of a linear code is the weight of the smallest non-zero code. But that certainly depends on which representation I use for the field. What we will show is no matter which representation you use for the field, most of these C alpha will actually be good codes. It doesn't really matter which representation you use. Most of them, whichever representation you use, most of the C alphas are good codes, and hence it will plug in with the previous observation of Justesen and you will get strongly explicit. So
So here implementation of F2 party with user F2 basis over
choose an F2 basis, yeah. Choose any basis, any basis. So the lemma which we are going to do is for all epsilon sufficiently large. At least n is the same n as before. At least 1 minus epsilon n of the inner groups. C alpha alpha and F star. Distance. What's the rate of this code is so E C alpha record C alpha. So C alpha is a 2TT code. What we'll show is for that rate, what will Gilbert Washam will tell you, it should be H inverse of half minus H inverse of half. We'll basically say most of them have distance. H inverse half minus 6. There's a fractional distance. So that's the plain lemma which we will prove. We'll take 5 minutes to put this one. But I want to say once you put these two codes together, the final code is an extremely simple code. What's the code? You're taking a Reed-Solomon code. What's a Reed? So what's a Reed? So let's look at what's the concatenated code. What's the final Justesen code? Justesen code obtained by concatenating Reed-Solomon with Wozencraft's ensemble. So I want to now explicitly give you what the code is. So recall the encoding for I'm going to give the encoding map. The encoding map. What was Reed-Solomon doing? It viewed the message, viewed the input as a coefficient of a low degree polynomial, evaluated it at various points in alpha. So it looked at the message, the input m, some m0, m1, m2, mk minus 1. Interpreted this as summation mi x power I. It maps m. The Reed-Solomon mapping is going to map it to m alpha, alpha in x string. It's the string. What's the next map going to do? It's just going to output m alpha. Wozencraft. It's just going to give m alpha, alpha m alpha. That's the entire. So that's the the code. So it's a super, this certainly will be, except it's a super explicit code. There's nothing fun. All the brute force search is going to be thrown into the analysis. So you say most of the C alphas are good codes, and that's where the distance is. So the Justesen is basically throwing the brute force search which we had into the analysis of the distance rather than the explicit construction. Okay, we still have to finish the proof of lemma. Let's go to proof of. Okay. So let xy be anything a non-zero string. I want to ask how many of the C alphas are bad, don't have good distance. I want to say if I give you an xy which is not the all-zero string, this xy can be in the image of at most one of the C alphas. Is that clear? I want to make the following observation. Xy is in the image of at most one of the C alphas. Huh?
C alpha is the alpha is one.
Alpha is 1. So y by x is 0. If x is 0, certainly it's not, and y is certainly not 0. Cannot be in the image of any of them. So if x is non-zero, the alpha is usually defined to be y by x. And so if x and y are both non-zero, it has to be in the ensemble P of y by x. And if either of them is 0, it's not in. Either of them is. If just one of them is 0, it's not in any of the images. So every xy which you have is in the image of at most one C alpha. So all the non-zero, everything in the non-zero point is here. What has the property? It has sort of, if you take off the 0, point, all the other guys, the images of C alphas are all disjoint. So given a particular point in the xy, you know it's which C alpha is the image of the C alpha. So, but what? So that's one observation. So this observation tells you that if you look at the space of 0, 1 to the 2, you can just knock off the 0, 0. 0, 0 appears in all the C alphas. Just knock that off. The rest are a partition of the images of C alphas and things which are not images of any of the C alphas. It's a partition. There's no overlap among the images of the C alpha, but for the all zeros. But what is it? When is the C alpha good? If it doesn't have any low weight code word, that's when a C alpha is good. So I want to, the number of low weight code words is small. Therefore, the number of C alphas also are, which are we know the number of low weight code words globally is small. That's just the volume count. Therefore, the number of C alphas which have low weight code words should also be small. This doesn't matter which representation you use. You know that the point is, Wozencraft ensemble is extremely explicit ensemble, except that I do not know which of the C alphas are actually good of them. That is, no matter which representation you choose, most of them are good, but I don't know which one. It will be actually good to find out a particular C alpha for which it's true. We don't know how to do this. What I want to say is, so because of this, the number of alphas in F star such that C alpha has distance T of P alpha is less than or equal to H inverse of half minus epsilon is certainly less than the number of xy in 0, 1 to the 2t minus 1 such that the weight of xy is less than or equal to H inverse of half minus epsilon times 2t. Just because if it is bad, there must exist at least one. And this one can only account for that guy bad. It can't account for more than two of them being bad. Of course, this might be a small, because if they're bad, there may be multiple of them, this might be an over bound, but still it's an upper bound on the number of bad P alphas. But this one we know exactly what it is. This number is strictly less than volume 2 n H inverse of half minus F. So this is not substituting. What was that? This is less than or equal to 2 power 2t half minus epsilon. That is 2 power t minus t 1 minus epsilon by 2. Yeah. But sorry, words. Therefore, what is the probability where an alpha in F star that the DC alpha is less than or equal to H inverse half minus epsilon? This is certainly less than or equal to 2t 1 minus 2 epsilon by 2t minus 1. This you can make for large enough t, you can ensure that this is less than epsilon times 2t. Sorry, just epsilon. For large enough. That's the end of Wozencraft ensemble. It's basically throwing the hardness of brute force search into the analysis. If you don't know which of these the alphas are good, most of them are good, but that's enough for maintaining the force concatenation. Okay. So this one is certainly super explicit. So you can't, this is as explicit as you can get for a one. Now you can check whether you can, so I did this for a specific choice of rate and distance. You can find out for which rates and distance does this, draw the curve and find out where does it match the this one. If you do just do whatever I do, you don't match the Zyablov bond fully. That is, you match the Zyablov bond as long as R is greater than 0.31 or something. Otherwise, for some reason, because the inner code, the Wozencraft ensemble has to have rate at least a half. Rate smaller than half. We can't have a rate larger than half. And that runs into some issues. But there are ways to fix this, and today we know so strongly explicit codes that completely match the Zyablov. So Zyablov bond not only can be equated with explicit codes that we saw for Forney's construction, but we also have strongly explicit. This gives you strongly explicit for a certain choice of rate, but after that we need a little more, we need some multiple geometry codes to implement, but with those can get really good. So the Zyablov curve is something in which you can get codes as good as you want. It's strongly explicit. So the next question is, once you have these, can these codes be equipped with good decoding process? Can I decode all the way up to the distance by 2 and stuff? You can ask to have good codes. Now can I equip them with other codes? And we'll see some of this. What we'll do in the next lecture is, suppose a code had concatenated code, we'll ask for what can we decode concatenated code. Suppose I give you a decoding process for the outer code and a decoding process for the inner code. Can I use both of these together to do decoding for the concatenated code? It seems obvious, but that you can do it. You just do the obvious thing. If you do the obvious thing, you will only be able to decode up to, suppose you have decoding all the way to distance by 2 for the outer code and distance by 2 for the inner code. You have the best unique decoding for the outer and inner. Question is, can I use these two to get the best decoding for the combined, for the concatenated code? To do the obvious thing, you will get the concatenated code, you can decode up to distance dd by 4. You should be able to decode up to dd by 2. That's what unique decoding will say. And 4d actually gives the decoding process. It says that the code has one other property, then actually you can make this decoding actually not just work up to DD by 4, all the way up to DD by 2. And that will be the focus of our next section. Let's stop.